All right, so the last chapter that we're covering in Physics 110 is on the concept of oscillations. Okay, and what we are interested in doing is mathematically modeling how oscillations occur. And oscillations come in a lot of forms. For example, we're going to look at the concept of springs. Yeah, there's a lot of systems that oscillate. A spring, a block on a spring. If you pull it out, it oscillates back and forth. Pendulums oscillate back and forth. There's just countless different types of behavior that all oscillate back and forth. And so one of the things we're interested in doing is being able to properly mathematically model that behavior. So this chapter, these next two lectures here, is going to be heavily focused on trigonometry. So you can see in the picture up here, I have different oscillatory motions. These are positions graphed with time. We got like what appears to be somewhat of a step function. We got a sawtooth function there, and the one at the bottom is the sinusoidal function. Now, from a mathematical standpoint, sinusoidal functions are very easy to model because they involve sine and cosine functions. Now, the principles that we'll talk about will certainly apply to the graphs that lie above it. They're just not, they don't have as convenient of a mathematical formulation. So you could treat those things, but they're just not going to be as easy to do. Now, one really important aspect of oscillatory motion is be able to characterize the period of the system. And the way that you want to interpret the period of the system is that it's an amount of time per cycle. So say you have a giant disk that rotates. If it takes 4 seconds full rotation, we would say that it has 4 seconds per cycle. 4 seconds per cycle. Closely related to that is the concept of frequency, which is given by a lowercase letter f. And that is very similar to period, except units are inverted. And the units there are cycles per second. So for example, if you want to talk about like that disk I mentioned, if the period is 4, the frequency is going to be 1 over 4, or 0.25 cycles per second. So there's a quarter of a cycle that happens in a given second, and that would be what corresponds to the frequency. And we have special units for that. Inverse seconds, which are ultimately what a cycle per second is the unit of hertz. Hz is the abbreviation for that. And so these things are both used interchangeably. Now, one thing I want to make you aware of, to make sure you don't mess something up here, is there is a difference, a significant difference between what is known as the frequency and what is known as the angular frequency. You've dealt with angular frequency quite a bit up to this point. It's the omega, which is units of radians per second, whereas oscillatory frequency, or just frequency just by itself, if the word frequency exists by itself, it automatically implies a hertz, not a radians per second. Okay, so be very careful with the language that you see. All right, so to start off our discussion here, I think one of the simplest ways we can view oscillatory motion is by looking at, say, for example, you have a mass that's attached to an air track. The idea with the air track is that there's basically very little friction on the air track, so the air track can move back and, the block can move back and forth, oscillating back and forth. And if we assume that we don't have any dissipative forces here, no friction, no drag, then the object will oscillate indefinitely in this configuration. And that kind of motion is a special kind of oscillatory motion we refer to as being simple harmonic motion. Sometimes you'll see the abbreviation SHM. SHM is simple harmonic motion. And so you can see in the bottom here, there's a graph, a position versus time graph. So the time flows as you get further, as you go down on the graph, and we can get a good sense of the mathematical nature of the graph. And you can see it resembles sines and cosines here. The maximum displacement from the equilibrium position is what we refer to as the amplitude, and we use capital letter A to indicate that. Okay, so how we're going to do this is the following. We are going to model this stuff with sines and cosines. And it doesn't really matter which one you use, because if you remember things from trigonometry, the only difference between a sine and a cosine function is a phase difference, which in the context of the problems we're talking about is just considering when things start. You just consider it starting at a different time or something like that. But it's commonplace that we use cosines to represent our functions here. Now, that won't always be the case. There may be situations where we want to use sine to start everything off. But the reason why we like to use cosine is that it starts at its maximum value. At t equals 0, the value of the wave function, if I want to call it that here, is the amplitude. So this is a common way that systems start. For example, if you take that block that's on the spring and you pull it out to a particular maximum displacement and you let it go, that motion can be modeled with the cosine because it will start at the amplitude, and then it oscillates back and forth about the equilibrium position. Okay. The other aspect of the cosine graph is that it has what's called omega t in it, and the omega is the angular frequency. Again, that's units of radians per second. And the difference between frequency and angular frequency is there's a 2 pi in the angular frequency. And what that does is allow you to convert a unit of time into an angle. So the space, for example, of the cosine function wants angles. So we're converting time into an angle, where the time is some part of the period of the object. Now, there's a lot of equations that you're going to encounter in this chapter. Tons and tons and tons of equations. And what I recommend is you may want to, as you know, if you're watching this in a video or you're just paying attention right now in my live lecture here, you may want to start to set aside a piece of paper, a notebook or something, and write down all these equations, because there is quite a bit that we have here. So omega is defined as 2 pi over period. But we already have a statement for what the period is in terms of a frequency. So another way to write omega is to put it as 2 pi f. And in our problems, we probably have an equal number of problems that are concerned with frequency and an equal number of problems that are concerned with period. So exactly what form you use is just kind of based on what information is given or what is easy to calculate or something like that. Okay. So now this is not going to be the complete sinusoidal function that we're going to use here. There is one more aspect that you can incorporate in here, and that is a phase shift, and we'll cover that a little bit later in the lecture. Okay. All right. Now, there's a lot of kinematic aspects to this that we care about. If we can characterize the position, say, and again, I'm always going to refer to these examples as the cart that's attached to the spring, right? So we can always have, I'm always going to refer to that, but obviously this can refer to any kind of sinusoidal motion. But if you have an equation that represents the position of the object, then you automatically know, actually, what the velocity and the acceleration of the object is, because you can take time derivatives. So taking the time derivative of the cosine function, okay, it's going to turn that into a minus sine. That's what the derivative of cosine is, minus sine. And a factor of omega comes out to the front as a result of the chain rule. So our statement, our function for the velocity at any given moment is minus a omega sine omega t. Now the coefficient that sits in front of the sine function would represent the maximum value of the speed. Okay, so you remember the behavior of both sine and cosine is that they vary between the values of 1 and -1. The maximum value of the sine function is 1, so therefore the coefficient that sits out front does represent the maximum speed of the object there. Okay. Okay. Now let's think about this equation and see that it makes sense. In fact, that might be my next slide. It is my next slide. All right. My brain's in sync with my brain from many years ago when I made this stuff. So that's good. All right. So let's pay attention to what's going on here. At the top, we have, on the upper right, we have a graph. It's a cosine graph of some sort of system that's oscillating back and forth. You have all the numbers here. You actually could construct what the graph of this function is. Remember, it's, I'll write it up here so you can see how that's going to look. Text. So it's going to be x of t is a cosine omega t. I'm using w. But we're given what the value of a is here. It's 0.17, the cosine, and then we are given a value for the period. Now, if you want to figure out what omega is, that's going to be 2 times pi times the time. Now that's the variable here divided by the period, 1.60. Okay, so this function, this is the equation of this graph here. We just inserted what our a is and what our omega is. Remember, omega being 2 pi over the period. So if you were to graph this, you would get exactly what we see here. Now, when we look down the velocity graph is exactly the derivative of the top graph. But in terms of the physical characteristics, let's make sure this makes sense. So imagine that we have this spring here, and I'll try to draw this out. So say we have this frictionless track, and we got our block here, all right? And say the block has been pulled out, and I'm going to draw a spring here, which, don't laugh, it's my best spring. Can't do them too good. All right, but say, for example, the equilibrium position was, say, right here, and we pulled out the block to the right as much as we can, and what's going to happen is the spring is going to try to restore its position, and so we initially have a velocity that's to the left. Okay, so let's look at what the sine function tells us. Well, it tells us that t equals 0. When the displacement is the greatest, we're going to have a speed that is initially 0. That's true. The moment we let go, it's not moving initially, but it starts to accelerate as it moves to the left. And then what happens is it reaches a maximum speed, but that maximum speed occurs when it gets to the equilibrium position. So again, I'm going to draw these lines here so you can really see how this looks, but right when the position becomes 0 is when you get your maximum speed. And then it moves to the left, and it gets to the other side. And when it reaches the other side, which is the next line right here, you can see there's a dashed line already drawn here. That's when it goes back to being a speed of 0, and then it starts to move to the right. So we see a positive velocity. When the amplitude, when the position gets back to 0, again, we have our max speed, and so on. So in terms of the physical characteristics, the position and velocity graphs make a ton of sense. Okay, so it's good to sort of look at both of those and understand what's happening there. Okay, let's keep going. All right, so let's get into a problem right away. Let's bring up my notes here for that. All right, so we got an air glider attached to a spring, oscillates between the 10 centimeter and 60 centimeter mark on the track. The glider completes 10 oscillations in 33 seconds. What are the following things? All right. So we have information here about amplitude. We have information here about period and frequency. Okay. 10 oscillations in 33 seconds would be 10 cycles per 33 seconds. So if I divide 10 by 33, that would give me units of hertz. And that would be what the frequency is. Now, the other way to do that is with the period. 33 seconds over 10 cycles gives you 3.3 seconds per cycle. So that is the period, 3.3. We invert that to get the frequency. So inverting that gives us this repeating decimal, 0.30, on and on and on and on. That represents the number of cycles per second. Okay. Angular frequency is given by 2 pi f, or 2 pi over the period, I went with F here, so 1.9 radians per second. The amplitude. Now, the way we figure out the amplitude is how far it gets from equilibrium. Now, the equilibrium position would be directly in the middle of 10 and 60 centimeters. So what you would do is you want to subtract them. The full range of positions that the block goes through is 50. We divide that by 2. That means 25 on either side of the equilibrium position, and therefore that's the amplitude. The actual equilibrium position would be 35 in this case. Okay, we have to offset that because we're not oscillating through like 0. We're oscillating through from 10 to 60. But you can get the equilibrium position. You can just figure out how much above and below that you get. So here we get 25 centimeters for that. And the max speed is given by omega A. So we have our omega from part C. We multiply that by the amplitude that we just have. And for this case, it's perfectly acceptable to leave your units in centimeters per second. That's generally okay in these problems. Like the stuff that sits out in the front of the cosine and sine functions, if it's in centimeters, it's fine. You can leave it in centimeters. That's okay to speak that way. I mean, if you want to be safe, make sure everything is SI, but you don't need SI necessarily for the speeds here. Not necessarily. Okay, let's move on. Okay, so now, one of the reasons why this works so well is because the concept of the block going back and forth on this track here, we're modeling that with sines and cosines, but sines and cosines were largely derived from circular motion. But that really is what's happening here. We are dealing with circular motion in a sense. So if, like showing the example here, we have a ball that moves around on a disk. And if you look at the projection of the X or Y positions of the ball, you do see that it matches up precisely with the behavior of the block. The fact that we're using sines and cosines means we can model a lot of behavior that ends up being effectively the same physically. Okay, the shadow of this ball is physically the same as a block oscillating back and forth. There is no difference in terms of the mathematical description of these things. So sines and cosines are useful for a lot of stuff. Circular motion, yes. Motion back and forth, like for the block, yes. I mentioned we're going to look at oscillations in terms of a pendulum later. That works too. Okay. Now, there's one other element to these functions that we could incorporate that is going to be, honestly, it is a common feature that will show up in these graphs here, and that you don't always start at your amplitude. Like, for example, the cosine function, you may have a situation where you don't start at their maximum displacement when t equals 0. What if you have something in between? You're looking at a system and you want to make t equals 0 at some arbitrary point. Well, you would have to incorporate a phase constant in order to do that. Okay, and so incorporate a phase constant just basically takes the omega t, which is the argument of the sine and cosine functions, and it adds in a constant factor. Now, we label that here phi naught. Okay, phi naught. And in order to figure out what phi naught is, you have to be told what the initial conditions of your object is. You'd have to know some information about how the motion starts. And so you'll need to be very mindful when you read over your problems, whether you have to incorporate a phase constant or not. Again, you would have to incorporate a phase constant if in the description of the motion it doesn't seem like it's going to start off the way a cosine function behaves. Or you're just directly told something like at t equals 0, the position and velocity are these values. And then you solve for their phase constant just given the values there. And I'll do some examples so you can see how that works. But this is a really nice illustration of how phase constants change the look of your graphs. And so in the first example here, we have a positive pi over 3 phase shift. And so what that's like, it's like we've started a little bit ahead. We didn't start at the amplitude, we started a little bit past that. So if you imagine, if you look at the graph for the cosine function for the position here, it's like you took your graph and you shifted it to the left, which is like we're starting a little bit ahead of what we normally would do. And then the motion continues from there. If we had a minus pi over 3 radian phase shift, that means we're starting like a little bit before the amplitude. So we're already moving to the right and we're approaching the max position there. So it's like taking your cosine graph and it's like shifting over to the right. A phase shift of pi radians is a complete 1/2 cycle push forward, basically. You started a complete half cycle ahead. So it's like you started off on the left instead of starting off on the right. So you could put a plus pi for the phase shift, or you can simply recognize that it's a cosine function that's been flipped vertically. And so you can just stick a negative in the front. And so your equation could be minus a cosine omega t, and that automatically incorporates that pi radian phase shift there. Of course, if the graphs are not, the ones for pi over 3 don't have any simple ways to rewrite the things, but multiples of pi over 2 do. If you have a positive pi over 2, that's equivalent to a flipped sine. If you have a negative pi over 2, that's equivalent to a standard sine function, and so on and so on. So if you can see that stuff, that's great. It's a convenience. It helps you out in your problems. But let me actually show you how you would numerically figure these things out. All right. So think about this for a moment here. I'm going to give you some time to... So what is the phase constant here? So, I mean, this looks like a sine function, right? So the phase shift here is going to be minus pi over 2. Now, there's a couple, I can give you one really quick, easy way to conceptualize. Well, maybe I shouldn't use the word conceptualize, but if you have a positive phase shift, what that's going to do, it's going to shift your cosine function to the left. Negative phase shift is going to shift your cosine function to the right. So now pi over 2 is exactly a quarter of the period. So, your cosine function normally starts right up top here, this little spot right there, but we've actually been pushed forward. So it's like we've started. So what this is in terms of, say, the block on the spring, this is equivalent to having the block right at the equilibrium position already moving to the right. That's a quarter cycle behind how we normally start things. And so because our cosine graph has been shifted to the right, that would correspond to a negative phase shift. And you can tell here from the graph that's exactly a quarter period. Okay, so all right, moving on again. All right, so think about this one here too. What do you think the phase shift's going to be here? Again, maybe we want to pause the video, but the answer here is oh, whoops. Pi radians. Well, guess what? That was back here. That's the graph that's on the bottom right here. But what does this look like? It's a flipped cosine. You can also view it as being a cosine that's been shifted a half cycle to the right or to the left, honestly. You can do either one because we're right in the middle of that. But that's consistent with being a quarter cycle difference. So what happens is we start off to the left. It's like we pulled our block out to the left and then we let go and then it started oscillating left and right. It starts off with the speed of 0. So. Great. The figure shows 4 oscillations at t equals 0, for which is the phase constant minus pi over 4. Minus pi over 4. So, another thing you can remember about phase shifts is negative phase shifts are kind of like starting a little bit in the past. Okay, the normal cosine function starts off with a position of A, and the block moves to the left. So a negative phase shift is going to put us a little bit behind in terms of moments in time from that motion there. So think about these here, and you'll see that the answer here is C. C is the correct answer here. So this is an eighth of a cycle. We're an eighth of a cycle before we normally start things off, so we have our block here that's already moving to the right, and it has a position that's positive. Okay, if we go another pi over 4, in terms of our phase space here forward, that would put us at a position of maximum displacement. So, all right, we want to determine the amplitude, the frequency, and the phase constant of the oscillation shown. All right, so let's jump right into that. Okay, so the amplitude's pretty easy and straightforward. It's how far above and below, right, the graph gets from equilibrium. The equilibrium is clearly at 0, and we go 20 centimeters above and below, so the amplitude is simply 20 centimeters. The frequency, you can read from the graph, it appears that the cycle, the length of time for the cycle is 4 seconds. It's 4 seconds to complete a cycle, so that's your period, and so 1 over 4 would be your frequency. Again, that's the F, not the omega, because it just says frequency by itself. So 45 hertz is what that is, but that can be multiplied by 2 pi to convert that into an angular frequency, which is what you actually do see down here if you look. I decided to actually write this out as an equation. That wasn't something that was required in this problem, but I think it's useful to do it. But the right here, that is 2 pi f, and that's how we get to this first thing here. That's omega. Of course, my amplitude's here, and that's what sits in the front here. Now, in terms of a phase shift, well, mathematically, here's how we do it. We are looking at what happens at t equals 0. Okay, so if you go back and you look at the two equations I had lined out for x and v here, you put in a value of 0 for t, and then your equations turn into the set of equations that you see here. The initial position equals a cosine theta naught, or phi naught, sorry, and the initial velocity is minus a omega sine phi naught. Okay? And so what we can do is you just simply plug in your values here. We can see that we start off with a positive 10, okay, for our initial position. That gives us a cosine that's equal to a half. Now, the way the cosine function works, though, is that that value of a half can either occur at 60 degrees or minus 60 degrees. So I put in radians here, so it's either pi over 3 or minus pi over 3. How do you know which one to do? Well, this is how you know. According to the graph that we have here, right at t equals 0, when the block's at 10 centimeters, we have a derivative right here. Look at the derivative here. The derivative is, again, the tangent line right at that location. And that tangent line, can I make it thicker? Make it thicker here. That tangent line contains a positive slope. So that means we have to pick the phase shift that gives us a positive velocity. So if you plug, for example, positive pi over 3 into your sine function, you get out a positive value, which when you combine with the negative in the front here would give you a negative speed. So that's wrong. If I put in a negative pi over 3 here, then what comes out of the sine function will be a negative value, which will multiply with the negative that already exists in the front, and you will end up with a positive speed. So it appears that our phase shift is minus pi over 3, and that makes sense again because if you have a negative phase shift, remember, it's like you shifted your graph to the right. That's another way you could figure this out too. You just look at your graph and say, oh, it's a cosine shifted to the right, therefore it's a negative phase shift. But mathematically, you would do that here. You plug it in your initial position. You will likely get out two values that satisfy the equation. One's going to work with the velocity and one will not work with the velocity. We want the value of the phase shift that actually corresponds to a positive initial velocity, and that happens with the negative pi over 3 phase shift. Okay, so my guess is you're going to probably have to rewatch this clip like 3 or 4 times, but that's okay. Whatever it takes to get it to sink into your head. It's a weird thing. It's not weird. It's just well, it just may take you a bit of time to think about all those details. It's a lot to take in at once. I know. All right. Oh, all right. Another problem right off the bat here. Let's do it. Oh, where am I? Here am I. Okay, so an object in simple harmonic motion has an amplitude of 4 centimeters and a frequency of 4 hertz. At t equals 0 seconds, it passes through the equilibrium position and it's moving to the right. Moving to the right. All right, we want to write a function x of t that describes the object's position. Well, we are given the value of a. Okay, that's easy. We're given the value of f. So omega is 2 pi f. That's going to be 8 pi. So I got the first two pieces, 4 cosine 8 pi t plus the phase shift. Well, if we're at the equilibrium position, that means the initial position is 0 and the initial speed is positive. So you're asking yourself the question, what values of cosine are going to give you 0? You want the two values that are the closest to 0, and that would be plus or minus pi over 2. So the phase shift is plus or minus pi over 2. So then we look at our sine function and say, okay, what value would make sure we have a positive velocity? If we plug in the positive value, sine of pi over 2 is positive 1, and that would give us a negative velocity. That's no good. If we put in a sine of negative pi over 2, that's going to give us a negative 1, which combines with the negative in the front to give us a positive value. And so that would be the correct one to use, negative pi over 2. Okay. Another way to know that we chose the right phase shift is this. A negative phase shift, it's kind of like taking a position or taking a snapshot, so to speak, in time that occurs before the standard starting place. The standard starting place is that the block is already out at the maximum position and it's about to move to the left. We're exactly a quarter cycle behind that because we're already we're in the middle and we're approaching the right. So we are a little bit backwards in time, and that would indicate a negative phase shift. Of course, you'd have to still figure out, what the actual value is by putting in 0 for the initial position. But anyway, it's another way to do it. All right, fantastic. All right, so other concepts here that are helpful in solving our problems is energy. So if we have a system, and again, if I choose the block, now, by the way, when I talk about this stuff now, this is specific to the block. You cannot say what I'm going to say here for other systems unless you characterize what their appropriate potential energy is. Okay, when we're doing conservation of energy here, assuming there's no drag and there's no friction, what we have is we have an energy transformation that goes back and forth from potential to kinetic, potential to kinetic, potential to kinetic. But the potential energy is specific for the spring here. It's 1/2 kx squared, right? So the stuff I'm talking about here, it only applies to springs or anything that we can describe as a spring constant. If I have a different system like a pendulum, or if I'm talking about oscillations due to gravity or electricity and magnetism, I'd have to figure out a different potential energy function. Okay, but for this, we know what the potential energy function is very straightforward here. So the total energy of our system at any moment in time is going to be the sum of its kinetic and its potential. So 1/2 mv squared plus 1/2 kx squared. Okay, and we can analyze this at any point, and we know that the total energy of the system is constant. It does not change. So if you want to be able to solve different aspects of the motion of this object, you can simply take a position that is known and compare it to a position that is unknown, or a speed that's unknown, and you can figure out your unknown quantities here. So let's see how that's going to work. Okay. So at any given instant in time, you have the top relationship here. At any instant in time, you can characterize the total energy of the system if you know its position and if you know its velocity. There are a couple places where there are special values for this. If we evaluate this expression when we're at our maximum position, that means everything was converted into potential and there's no kinetic. So the kinetic becomes 0 and the potential becomes 1/2 Ka squared. Okay. If we consider through the equilibrium position, the position is 0, therefore the potential energy is 0, and our speed is at the maximum value, so we can write our total energy as 1/2 m v max squared. These three things I've boxed here, right? These three expressions here are all identical. They're all equal to each other because they're simply different snapshots in time of the same system. So you can equate any one expression with another expression, okay? And that's how we generally solve energy conservation problems, is we usually equate one of these with another one to solve for something that's missing. Now, one thing we're going to do here, though, oh, I guess we're not going to do that yet. I got a question for you first, so look over this, and then we'll talk about it. All right, so think about this for a minute here. What you're looking at is you're looking at a kinetic energy graph. Of course, you have some kind of system energy here, and I can draw that for you. The system energy is up there. And so if you have any difference between the system energy and the kinetic, guess what? That's potential energy. So the bottom portion here is the kinetic. The rest of it is the potential energy. So we see we're going to shift between back and forth, back and forth. So the total system energy here happens to be 8 joules. Okay, so the spring constant's going to be going to be 4 newtons per meter. Why? Because if my total system energy is 8 joules, I can equate that to 1/2 Ka squared. That is one expression for what the system energy is. I know my A comes from the graph. It's 2 meters. So I solve for K, and we end up getting a 4 out of that. So it turns out the spring constant here is 4 newtons per meter. And that's just using energy conservation to solve that. All right, so what I'm going to do is I'm going to go back to the equations here. I'm going to take my two bottom equations and I'm going to put them equal to each other, and I'm going to try to simplify this as much as I can. Now do realize that the V max, we already know what that is, right? That's equal to omega A. So I'm going to set these two equal to each other. And you can solve for V max, and V max is this expression right here. But V max is equal to omega A. So if I plug omega A into the stuff over here, the A's drop out, and I end up with this really, really nice expression that, again, only applies for springs. But it basically, actually, all three of these work here, but we immediately get the first one. But we can see how we can characterize the period and the frequency of our system here. As long as you know just the mass of the object oscillating and the spring constant, that can almost entirely characterize for you how the system behaves. That tells you your omega, which is a big part of the system here. But what's fascinating about this actually is this. If you look at that last expression for the period, it says period equals 2 pi square root m over k. So when you ask yourself, what determines, if I take this block and I pull it out and I let it go, what is going to determine the period here? Well, it turns out only two things determine the period: how much mass there is and what the spring constant is. Okay, what do you not see here? What you do not see here is the amplitude. You don't see that. And the amplitude ends up not mattering. If we pulled this thing out to 1 centimeter and let it go, it's going to oscillate with a particular period. If I pull it all the way out to 1 meter, not 1 centimeter, it's going to oscillate with the exact same period. That may seem surprising, You would think that if I pulled it out more, it might take longer. Or maybe you think it takes shorter, but it doesn't. It doesn't change it at all. The period is determined exclusively by mass and spring constant. Okay? You saw this sort of. One of the labs we did before the campus closed was the pendulum lab. And you remember that one of the things we learned about that was the period of the pendulum is dependent on the length of the pendulum and the gravitational constant. That also did not have an A in it. How far you swung it out didn't really determine the period much, other than if you swung it out too much, the equation wasn't valid. You have to use a slightly different equation. And you'll see why that is in the lecture on Tuesday. Because we'll actually get into how pendulums work. We'll derive that equation, but I'll show you how it's an approximation. Okay, so we'll see that later, though. All right, so think about this question here. We have a mass oscillates on a horizontal spring with the period being 2 seconds. If the amplitude of the oscillation is doubled, the new period is going to be... What do you think? Well, this question is basically, did you listen to what I said literally a minute ago? The period is not changed because the amplitude does not determine the period. Okay, block of mass m oscillates on a spring with a period of 2 seconds. If a second identical block is glued to the top of the first block, the new period is going to be what? All right, well, what this does, gluing it to the top, may sound like a funny thing, but the problem is trying to communicate to you that we've basically just doubled the mass. So why didn't we just say double the mass? I don't know. I should probably change this question so it's more clear. Anyway, it's doubling the mass. If we double the mass, that should make the period go up. And if you go back to the equation there, we see that the period varies as radical m. So if we double the mass, the period would increase by a factor of radical 2, which is 1.4. 1.4 times 2, 2.8. Great. All right. Two identical blocks oscillate on different horizontal springs. Which spring has the larger spring constant? Well, so the masses are the same. The spring constants are different. What information in these graphs are going to tell us something about spring constant? Well, you got to go back to those equations. You will see that period, right? Period equals 2 pi radical m over k. The m's are the same. So the longer period, because there's an inverse relationship between these two things, the longer period is going to have the smaller spring constant and vice versa. The shorter period appears to be the red one. So the red one's going to have the larger spring constant. Okay. And the interpretation of that is if the spring is stronger, right, it's going to oscillate more frequently. That makes sense. It's a stronger force effectively on it. So that's clear. A 200-gram air track glider is attached to a spring. The glider is pushed 10 centimeters and released. A student with a stopwatch finds that 10 oscillations take place in 12 seconds. What is the spring constant? Well, let's see here. We're given the mass. We're effectively given what the period is. We're told what the amplitude is, 10 centimeters. But remember, don't care about that. 10 centimeters, ignore it. What's the period? Period would be 12 over 10. So 12 seconds for 10 cycles, that is a period of 1.2 seconds. So we got that. We have our mass. You got to do SI stuff here. So the mass is going to be 0.2 kilograms. You take your equation for T, this equation that we have here, solve it for K, and we get 5.5 Newton meters. All right. That looks good. Last question. We are given a graph. Well, we're given an equation that represents the position of an oscillating mass. We're told the mass is 50 grams. We're told the amplitude is 2. That's the coefficient of the cosine. We're told what omega is. It's 10 radians per second, and the phase shift is minus pi over 4. So given that we have the mass and we have the full equation, we can determine all of these things here. Now the amplitude is whatever the coefficient is of the cosine function. So it's 2 centimeters. Simple enough. The period can be determined by a lot of things, but I think the easiest way to do that here is to use the 2 pi over omega, because we have omega, it's 10. So that gives us a period of pi over 5 seconds. I'm just going to leave it in terms of pi over 5. If you type in your calculator, that's great too. You probably should, honestly, but I was being a little lazy when I made this. We want to know what the spring constant is. Well, if we have the mass and we have omega, then we do have the spring constant. Okay, so remember the equation was omega equals radical k over m. So I square the equation, solve for k, and so it's omega squared times the mass. Again, make sure that you put the mass in kilograms. The omega, just make sure it's radians per second, but that's the way it is in the equation as it's given. Phase constant is just read from the equation. It's minus pi over 4. The initial conditions. The initial conditions is when t equals 0. So you plug t equals 0 into that equation up top there. And we end up with 2 centimeters times cosine minus pi over 4. And we get out our initial position, radical 2 centimeters. The equation for the initial speed is omega minus omega a sine, phase shift. Again, those are the equations we developed for the phase constant and the initial conditions. And we get 10 radical 2 centimeters per second. Great. We want to know what v of t is. And there's a lot of ways you can do that. You can just simply take the derivative of the expression up top. That's it. Pick the derivative of the expression up top. The other way to do it is to simply multiply omega times a together, and that represents the coefficient on your sine function. So you just replace your 2 with what the max speed is, omega times a. Make sure there's a negative in front of there, because that's part of it, and then your cosine becomes a sine. But honestly, the easiest way to do this is just take the derivative of that thing. That's probably easier, in my opinion. Max speed, that's the coefficient on the velocity equation. I wrote it in terms of a magnitude, so 20 centimeters per second. And I want to know what the total energy of the system is, so I can use any number of equations for that. And I just happen to go with 1/2 ka squared. That's what I wanted to do. I mean, you can use the 1/2 mv max squared. Doesn't matter. It all works. So I happen to go with the one that is 1/2 ka squared. I already have k from part, C? And I have my value for a. It's in centimeters, so I got to make sure you convert to meters, but we get 1 millijoule. That's a millijoule down there.